Let's go. Okay, I wanted to show you this reaction furnace and the reaction cooler that we talked about it over there. This is the model of it in front of me. This is the reaction furnace. This is the burner that I told you about. Okay, and I told you we don't have a pipe between them because it's too hot. It's a flange. And this is the cooler. This is a steam drum. The way we designed this cooler, the water goes in, we generate the steam. Okay, we have a steam drum there. It doesn't show here, but this is right here. This vessel you see here is at the top of this heat exchanger. The water goes in, the steam comes out, and the gas is cooled. Bring the gas to the condenser. Ashish, can you bring the condenser? We're going to go a little bit faster. When you get a picture of the process, then we can go faster. Where's the condenser? Just stay right there, show it when I... This is the... I said we cool the gas, we bring it here, we cool it again. This time, we want to recover the sulfur has been produced here, right? I said that we generate some vapor sulfur, we cool it, we cool it, we cool it here. This is the sulfur. We have a concrete pit, or some people wanted the carbon steel inside of the concrete pit. Underground, is free draining of the sulfur goes here. We call it sulfur pit. So the sulfur is condensate here. The boiler feed water goes in. This time we generate low pressure steam. And the remaining of the gas, we have now two-phase flow here. The liquid goes down, the vapor goes up. The vapor goes up, we have to have a reheater. Before we send it to the reactor, we have to reheat the gas. Why? Because we have some catalyst here. If the temperature is not adequate, nothing would happen. Okay? We normally put the reheater on the top, just like on the model that Ashish is holding. So we have condenser here, and we have reheater on the top that Ashish is showing the model. Okay? We heat the gas, and we bring the gas to the reactor. We call it converter number 1 or reactor number 1. Different project, we call it different things, depend on the client. Okay? Inside of this reactor is contained catalyst. This is the reactor. If the sulfur plant are small, what we do, we make them all in common shell, okay, with a divider. We normally do that if they are under 100 ton a day. If the sulfur plant are large, the reactors are become very large. Becomes too long to put it in one shell, so we make them separate. So the model shows, because it's just a picture, just a model, we show them as a common, okay? So in the converter, if you have a refinery type application, we use aluminum catalyst, okay? But there are many applications we get. We have a lot of bad stuff in the gas. The acid gas H2S concentration is low, or we get a lot of bad stuff in the reaction furnace, all the side reaction, you remember I said? Somehow we have to get rid of it. Then aluminum by itself cannot do the job. Then we have to provide it to add some promoted catalyst to help us out, to improve the recovery. Okay? So no matter what catalyst we use, then here, we make some conversion here. The sulfur species, we have some of them, again, convert to sulfur, just stage by stage. We cannot do it all in one converter. Some of you are chemical engineer, you understand the equilibrium condition. There's a limitation. You cannot do everything in one stage, all right? So we bring the gas, we cool it again on the second condenser, boiler feed water in, generate the steam, and recover the sulfur, and start again. We do that 2 or 3 times to get to maximum possible recovery we can get in the sulfur plant. This is a 3-stage sulfur plant. If you have tail gas unit, we don't provide the 3rd stage. It's not cost effective, okay? We only do 2 stage, and then we follow by the tail gas unit. Some of you may work on North American job. Someone in a break told me he just sized the air blower on North American job. Yes, the air blower for such a size, it's a very high horsepower. So if you have tail gas unit, just like we have on North American job, if some of you work on that, we only go up to here. The converter number 2 and the condenser, and that's it, we stop here. We provide 3rd stage. Some of the states required by law, they have to have 3 stage. Or they don't have tail gas unit, so they want to get the maximum recovery as possible. So this is basically the configuration of the sulfur plant. Any question?
The sulfur in the feed is which form? Is S or S2 or S3?
Well, it's liquid sulfur. You can consider it as S1 or S8. It's a combination, but to us, to the seller, because what happened here, there's a liquid sulfur here, okay? They pump it out, they send it to the storage tank, they can sell it as a liquid. In Canada, there are some places can buy it as a liquid, or they can solid it. In US, everybody solidified and sell it, okay? And the new regulation is they want to degas that before they get to this stage, before they solidify it or sell it. They need to, because there is some vapor space here, contain H2S, and it's very dangerous. And when they sell the sulfur, if it's not packed completely, it's just very dangerous. We have some sulfur, solid sulfur in Monrovia, in process library. So if anybody wanted to see how the sulfur looks like, and you may be surprised where did that sulfur come from. That sulfur was the very first sulfur plant we designed about 35 or 40 years ago in California at Shell refinery. At that time, it was not Shell refinery. And everybody was so fascinated about that. They put it in the glass containers in the library. If you get very close to it, it still smells H2S, but you don't want to do that. I told you that when we do sulfur plant, it's a very complicated control system. We couldn't show those on that first sheet. So all it shows control system. I'm not going to go through this, takes a long time to go through. But there is a lot of complicated control system about the control the temperature, control the rate, air, and everything. That everything controlled by DCS. This is some chart that help us on the flame temperature of the air for mixture of amino acid gas. It's the adiabatic flame temperature. That was about ammonia technology that I told you that we do bypassing. The same thing. We said that the sour water, the ammonia gas comes from sour water stripper. So it described that how it works. I talked about the refractory material. You remember I said the bare metal cannot handle it. So here is specified what material we do Okay? Oxygen burner plus oxygen burner plus waste heat boiler. It just defined that all the castable material we do. This is a picture of the reaction furnace here, like we talked about. This is a 3-dimension picture. The only things here, the burner is tangentially mounted, okay? We don't do tangential anymore. We do end firing, we put the burner here. But that's the old design, we used to do that. We do that only if the client requested us to do that. So you can see it shows all the detail of the refractory and all the break I told you is inside. It shows all the detail. This is a data from the CFD modeling. You remember I told you that we do ammonia burning and we guarantee. Well, if the process is very complicated sometimes, we have a lot of ammonia or the feed composition is not very typical, we get the burner manufacturing do 3D CFD modeling for us. So when they do CFD modeling, it shows that the way ammonia is burning. This is reaction furnace, this is a burner, and from the color, when they do CFD modeling, they can see the ammonia burning, okay? This again, you know, we provide the pieces of refractory in there for a better mixing inside of reaction furnace. Again, is our proprietary design. That is, we call it choke ring. So it shows that how velocity is important on the ammonia burning. And then we go to the tail gas processing that we talked about it. I mentioned that we use generic solvent like MDA, or we use proprietary solvent like Flexor, HS101, HS103. We have other technology that, you know, it takes a long time to go through all these processes, but if anybody interested outside of this class, I can explain too. We call it BSR Selectox, BSR Recycle Selectox, or Selectox incineration. All this technology offer for different application. When we see the application, we offer it accordingly. It is part of my responsibility that when we get inquiry, look at that to see what we have to offer. What is the suitable technology we have to offer for this application? And then we make our recommendation. Okay? I'm going to go to the tail gas unit to show you how tail gas unit. This is a configuration of the tail gas unit. You remember I said that in sulfur recovery unit that we get 95%, 96% recovery, and there are some leftover of H2S, and we have to do something about it. Okay, we bring those leftover here. Again, we have another system similar to reaction furnace we talked about, another fire equipment. But what we do here, we bring air and we use natural gas. Over there, we didn't use natural gas as a normal operation. Here we do, to heat up for heating purposes. And this is the leftover coming from sulfur plant. We call it Klaus tail gas unit. Okay? So we go here, we have a mixture, but here the combustion is not, you remember I told you over there we have a specific combustion, we want to convert 1/3 of H2S. Here is different, we use some other ratio of substoichiometric. Okay? We do that. This is, we call it reducing gas generator. I'll show you the detail of it next slide. Again, it's a proprietary design by Worley Parsons. You see this word may be RGG all the time, but this is an abbreviation for reducing gas generator. There are a number of purposes here. We heat the gas here, and as a result of the reaction happening here, we generate some hydrogen and CO. We need to generate that. We bring some of them from sulfur plant, but we need more. If we don't generate those here, then we have to have external hydrogen here. And I explain why later, okay? Okay, we have our reaction here. We have a hot gas, again the same range of temperature, about 3000. Here, directly we bring it to the reactor. Okay, but here is different catalyst. Actually, there is a cooler here is missing here. We bring it to the reactor, and in this reactor, a lot of components, you remember in sulfur plant, I said we make SO2. Okay, we convert all the SO2 back to H2S. We have to. We cannot make sulfur from SO2 directly. So what we do here, we call it hydrogenation reactor. By the hydrogen and CO as a reducing agent, we generate here. We take all the sulfur species, SO2, COS, CS2, whatever, we call it sulfur species, okay? We convert all of them back to H2S, okay? So what is leaving here, there is a very little amount of SO2 that we capture it by different method, but the majority is already converted to H2S. We cool the gas here, we bring it to this tower to remove all the water, because here, and also in the sulfur plant, we generate quite a bit of vapor water as a vapor, because it's hot, right? So it's not a water in shape of water, it's as a vapor. So we liquid here, we condensate all the water here in this tower on the top section. How we do that, we take a stream from the bottom, we cool it in the cooler, air cooler, and is really followed by another water cooler, heat exchanger. And we recycle it back. By doing that, the gas is coming here, all the water gets condensed at the bottom, and the gas goes to the top. Okay? Also over here, which it shows on the different picture, if there's any SO2, didn't convert it for any reason. Nothing is perfect, right? Word is not perfect. Maybe you get 20 ppm of SO2 or whatever you get. What we do here, we inject a little bit caustic to absorb those SO2. Okay? This is the RGG that I showed that in the previous picture. That's the detail of it. This is Worley Parsons' proprietary design. When we get a project from the client, we provide a mechanical design of this equipment by our mechanical group. Sulfur group size the vessel. Mechanical group cannot size it. We size it. We size this length, the ID, all the nozzle, everything. And mechanical group generate a mechanical drawing. So that when they give it to the client go and purchase it. They give it to the shop, and shop fabricate that. Okay? This is the tower I was talking about. The detail of the tower, that we circulate water, and then we cool the gas. And this is a description of that tower, how the tower works. Okay, we finished that. We come to the amine part of the tail gas unit. This has become a very typical amine unit that is very normal for process engineer, but those are not process engineer. That this part is an amine unit. So we repeated all the equipment that we talked about. Now we are showing entire tail gas unit. We talk about RGG, we talk about the reactor, we talk about the tower. Now, the gas was leaving. Remember I told you the gas, we removed the water from the gas coming to this vessel called absorber. And here becomes another tricky part. We have to see what solvent we have to use, again, to meet the regulation. We call it amine as a generic name. It could be generic solvent, it could be proprietary solvent. And we choose the solvent accordingly based on the inquiry we get from the client. Okay? So the gas is leaving this absorber, goes to the thermal oxidizer. So we have to guarantee this stream of H2S. Client may say 10 ppm of H2S or 100 ppm. So we choose the solvent properly. What happened here, we bring the gas here, we bring the solvent to the top, is a chemical reaction in the tower. Okay? The solvent absorbs the H2S as much as possible according to the selectivity solvent has. Whatever solvent cannot absorb goes to the top. So the solvent is rich of H2S and CO2 leave the bottom of the tower. Get heated up, pumped, go to the column called regeneration tower. In regeneration we have number of stages here. The actual stages is between 20 to 24 stages. Okay, we have a reboiler and we have a condenser. Okay, what we do here, we want to recover the solvent, right? Because the solvent now is saturated with all the H2S and CO2 absorbed here. We heat it up with the tray, with the reboiler heat. What happens is all the H2S leave the solvent, like you boil it, okay? You boil the solvent. The H2S leaving, we recycle it back where? To the sulfur plant that we talk about. So we recovered all this H2S, all the junk and stuff, right? So we capture it here, we recycle it back to the sulfur plant. So it's a closed loop, right? So all it goes to the thermal oxidizer or atmosphere is only this one. And this is just, could be from 10 ppm of H2S to 100 ppm, which define our recovery guarantee. And the bottom of the tower is a recovered solvent, whatever it is that we choose, right? We pump it, we cool it, we recycle it back to the absorber, and back and forth again. And of course we provide makeup solvent as required, because we have losses of the solvent. Okay? So by doing that, you can see with this drawing and the sulfur recovery we covered is a closed loop process. We recover H2S to 99.99. I hope I didn't confuse you. Any question? No question.
So, solvent can absorb SO2?
No, there is no SO2 left. You remember here we said in this reactor we convert all the SO2 back to H2S. If SO2 see the solvent get damaged. There are solvent can work with SO2, but not with this process. There are other solvents we offer, if you look at on the gas processing sheet, such as CANSOLV, okay? CANSOLV solvent. But for this application that we are offering as a licenser, it should be a solvent only works with H2S and CO2. Yes?
So is that the process that you described it, that if you're going to capture the SO2 from the flue gas, where you can actually send it to the unit to...
The SO2 from flue gas, we put it in the reaction furnace here.
And then it goes through...
If it's carried over here, some of the SO2 In the previous picture of sulfur plant, in the reactor, you remember we had aluminum reactor, some of the SO2 convert to sulfur. But if there's any SO2 left over, comes from sulfur plant, we convert it back to H2S right in this reactor. We call it hydrolysis reactor.
Is there any absorbent that can absorb the SO2?
If any leftover of SO2 at the range of ppm, we capture at the bottom of this tower with caustic. Because if SO2 get to this amine, it contaminates the amine. We cannot have SO2 in the amine. It's just you have to throw away the solvent. Just degradate. We call it degraded amine. You have to dump the equipment, empty everything, bring a fresh amine you need if you have a breakthrough. It happened in the refinery a lot because this part we do with the caustic is a proprietary design by Wally Parsons. None of the other licensor has this part. And they get a lot of breakthrough of SO2 in their absorber and regeneration, and they have to keep dumping the solvent and cost a lot of money. They call us and we say, okay, well, you don't have our technology. If you change this contact condenser to our technology, we can fix it here for you. We have a little bit caustic. We can absorb it. You can protect your solvent. That's why the design, when we do the design, we have to be very careful. Because if this one doesn't work, everything is screwed up. And if this one doesn't work, then we don't have any hydrogen and CO, the reactor doesn't work. So it's all related, piece by piece. You cannot compare and say, okay, the first equipment doesn't work, we do it in the second one. It doesn't work like that. Each one has his own job. Okay? It shows some of the data on the selectivity of the solvent, generic solvent versus proprietary solvent that I talk about. The same thing, some with Flexorb. Just talk about all the design features that we do in sulfur plant, differentiate us from the other licensor. So the way we do design and stuff like that. One thing I forgot to mention that at the end of the sulfur plant, we have an analyzer. We call it tail gas analyzer. And the gas is leaving the sulfur plant has to have H2S to SO2 ratio 2:1. All the reaction we done in the reaction furnace and everywhere and everything. You remember I said we have to calculate how much air we needed. After all the stuff we do, the gas leaving the sulfur plant has to have a ratio of H2S to SO2 2:1. And that's the key. So you realize that when we simulate sulfur plant, there are so many factors we have to check. This is a talk about, those are very detailed. I don't want to bore people who are not process engineer. So I'll talk about our design feature. Here you remember I talked about sulfur degassing? Okay, I summarized. There are 4 or 5 technology in the market. There are no more than that. One is from GAA. I told you that Gore Allison, that we have alliance with them, which is similar to Ameco. Ameco offered that technology, but we don't We don't have an alliance with them, okay? But they are pretty much identical. It's just that the operating pressure is different. And it describes what it does. Exxon at Shell, basically when we say sulfur degassing, we do sulfur degassing. We call it external degassing or internal degassing. Internal degassing can be done inside of the pit. If somebody wanted us to do the degassing from day one when we design a sulfur plant, then we size the sulfur pit so we are able to do degassing. But if we want to do revamp of the sulfur plant, the sulfur pit is not adequate. They have to go and change it, okay? In some cases, the refinery